these properties apply even if the 2 times t1 and t2 are extremely close to each other. Even if these 2 points in time are extremely close to each other, we can still divide the interval in n sub-intervals and take the limit as n increases to infinity. It is convenient to work with a small time interval, so we often define dt, which is difference of t2 and t1. Also, dx is difference of the xt2 and xt1. So we get this one. Change of x is approximately follows normal. It actually follows a normal distribution with mean 0, and variance is simply change of time. Simply change of time. This is important. Now we can represent a driftless whole model using a Brownian motion. So RT equals R0 plus sigma xt. And since x is constant, we can put it in differential form. So change of dRT is sigma dxt. It is driftless because there is no constant. We don't add any constant over here. So if there is no drift, a driftless whole model is dRT, change of interest rate, follows normal distribution mean 0 and variance sigma square and change of time. This is also very important. Since dx is n0 dt, we can write this in this way. Right? Here epsilon is normal distribution, standard normal distribution. So these three all follow same distribution. Particular, we use this notation a lot for future purposes. This is also important. Of course, this is important too. Let me define Brownian motion formally. The standard Brownian motion, often called Wiener process or even Einstein process. The standard Brownian motion, xt, is characterized by the following properties. x0 equals 0. X has independent increments, which means xt plus u minus xt is independent of history, i.e. xt plus u minus xt is independent of sigma xs, s is greater than x is less than equal to t. Here sigma means all the history generated by past x. So history before t is independent of change of x after t. That is what this second point means. Third, x has Gaussian increments. Gaussian increments means normal distribution, basically. Therefore, xt plus u minus xt is normally distributed with mean 0 and variance u, i.e. xt plus u minus xt is distributed with n0u. Here u is just change of time between xt and xt plus u. So the x has a continuous path. With probability 1, x is continuous at every time. So continuous means basically you can follow the path with your pencil without putting your pencil away from the paper. So it is continuous. You can draw the path in one line. But it's practically very difficult. I will explain shortly. But anyway, x is continuous. This is one illustration of Brownian motion. Here, we can find a very interesting pattern. This is a Brownian motion from time 0 to time 25. So, from 0 to 25. So maybe you are interested in very small segment. You are maybe interested in this very small segment. How does it look like? So you can magnify this one. Then it looks this one. Well, interestingly, this one exactly very similar to this one. So suppose you are interested in this small segment. Again, you can magnify it until you can find a lot of zigzag pattern. This is very interesting because when we define Brownian motion formally, we learn that this Brownian motion is continuous. It is continuous. However, for each segment, even if we magnify each segment, the same pattern repeats itself. So therefore, even we move from to here, the length of this distance, the length of this line is infinity because we magnify this one, we have the same zigzag pattern, magnify again, we have same zigzag pattern. So although it is continuous, same pattern repeating itself, therefore the length of any segment in the line is infinity. It's like map. So if you take a look at the sea line border between land and the sea of our peninsula, then it is complicated. Suppose you want to magnify a part of the map, and if you magnify it, you can still find a very complicated sea line. And if you magnify it again, it is complicated. So basically, it is impossible to measure the length of a sea line in detail. Exactly because as we go deeper and deeper, the same pattern, similar pattern repeats itself, so length is infinity. So this is a very interesting pattern or pattern of Brownian motion. This is another example of Brownian motion in three-dimensional space. In the previous space, it is just one-dimensional. It is a line. Brownian motion, it can either go up or go down in the next time. It is three-dimensional, so it can go up or down, left, right, something like this. And the path looks like a smoke. So in natural science or engineering, Brownian motion can be used. People use Brownian motion in order to explain the movement of the particle on the air, which is three-dimensional Brownian motion, or movement of particle in the water, on the surface of water, then it is two-dimensional movement, two-dimensional Brownian motion. Or in our case, like movement of stock price or interest rate, it is one-dimensional Brownian motion.